at mutual exclusivity. So whether or not whether or not two events are mutually exclusive or not. So let's get started. All right. So the first thing we want to take a look at here is we want to take a look at the definitions of mutual exclusivity. So what we have here is we have first of all, two events are mutually exclusive, and another word for this mutual exclusive is disjoint. So we can actually use a second word for this if we prefer. So disjoint. So two events are mutually exclusive if they cannot occur at the same time. So two events that cannot occur at the same time. So, of course, the converse of that is that two events that are not mutually exclusive means that they can occur at the same time. So there's your definitions out of the way. Okay, so mutual exclusivity is two events that cannot occur at the same time, and two events that are not mutually exclusive are two events that can occur at the same time. So we're going to take a look at this in particular with relation to the addition rule. Right? What you're going to see is, and we talked about this in the last lesson, is the addition rule. We've got to make sure that we're not counting the intersection twice, right? So if we actually look back at our Venn diagrams, right? The key idea here is that, and we'll look at two events that are not mutually exclusive first of all. So if we've got two events, here's two events, they're not mutually exclusive. We're going to say that they have something in common right here. Okay, so two events that do have something in common. If we're going to add up, the events here, let's put something into the events. Let's say items A, B, C is in common, D, and E. So if we were to add up all of the number of events in each, we would find, well, the number of events in A is 3 events, right? Plus the number of events in B is 3 events. And then we find that we have to subtract the number of events in C, or the number of events in A intersection B, right? If we're labeling this A and B, okay? I know a lot of use of A and B. This is not very proper, but hopefully you get the idea. We've got to subtract this, right, so that we get 1, 2, 3, 4, 5, so that we get 5 total, because this is going to give us 6. So we've got 6 minus 1 equals 5, okay? So generally speaking, what we're talking about is when two events are not mutually exclusive, they can occur at the same time, and you have to subtract that intersection. So I'm going to just erase that, and I'm going to kind of give you a slightly better interpretation of it, just in terms of those Venn diagrams. So if we look at those Venn diagrams, we could see, okay, here's two events that can occur at the same time. They've got something in common. Here, on the other hand, is two events that cannot occur at the same time. They have nothing in common, right? Okay, so this would be event A and event B, right? There is no intersection. Right? And in this case, events A and B, you can see here is a intersection B, and so we can't count it twice. Right? So that's the general idea of mutual exclusivity. You can add the probabilities together because with mutual exclusivity because there's no intersection, but if two events are not mutually exclusive, we have to remember to subtract it. So let's take a look at an example here. Right? First of all, let's choose one card from a deck of 52, and what is the probability that this card is both red and black? Right? So if we think about this, we think, okay, so the probability of a card being both red and black is 0. Okay, the probability of red and black equals 0, which means that the events red and black, so these being two different events, are mutually exclusive. And the great thing is you don't really have to think about it, right? So if you know that the intersection is equal to 0, you know that they're mutually exclusive, even if you can't figure it out just through thinking about it. Of course, with red and black, that's something that's quite obvious. So let's move on and take a look at a few more examples. Okay, so choosing one card from a deck of 52, what is the probability that it is both a king and black? So a black king is what we're looking for. The probability that it is a king and black, right? Well, there are 2 kings that are black. There are 4 kings, but there are only 2 of them that are black, so the probability that it's king and black is 2 out of 52, which, of course, if we simplify, that's 1 in 26, right? There's a probability. There actually is a probability that that you can be king and black, which means that events king and black, and so event king and event black. This is why I'm using the set notation here to kind of distinguish between the two. So the event king and the event black are not mutually exclusive. Okay, so just so that you're aware of all that. Okay, let's look at it with a little bit of math. So now we're looking at finding the probability of events that are whether events are mutually exclusive or not. Okay, so 2 different examples given probabilities, 2 different examples of events that are mutually exclusive or not. Okay, so let's take a look at this. Right, what we find. Okay, so we've got the probabilities here. If we go back to just looking at our addition rule that we had above. Okay, and I'm going to rewrite it out to you before rather than scrolling up. So remember our addition rule: the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersection B. And note that if the probability of A intersection B equals 0, then A and B are mutually exclusive. Right, you'll notice here now we haven't got A intersection B, so we got to figure this out. Okay, so what we can do here is we can say, okay, so we can apply this. This whole thing to the formula here. We can say, okay, well, to find out, we're going to go, okay, the A union B is 71 over 80. Right, and we're going to say that's equal to, or is that equal to, I suppose, is that equal to the probability of A, which is 3/4, plus the probability of B, which is 11/20. Now, just recognize here that if these are not equal, right, that means that we have to be subtracting an intersection here. We can actually find out the intersection if we want. It's not necessary right here. We just want to know whether it's mutually exclusive or not. But if these are equal, if 3/4 plus 11/20 equals 71/80, then these 2 events are mutually exclusive, right? Because there's no intersection. If, however, they're not equal, then we know that they're not mutually exclusive and that there must be an intersection that we need to solve. Okay, so let's take a look. Well, we're going to need common denominators. We're going to keep the 80 and just go with that. So we're going to say, okay, the 3/4 to get 80 we're going to have to multiply by 20 above and below, so that's going to give us 60 80ths. And this one here, we're going to have to multiply, to get 80, we're going to multiply by 4 above and below, so that gives us 44 20ths. Sorry, 44 80ths. Multiplying by. All right. And what we get here now is we're getting 104 80ths. And that, of course, is not equal to 71 80ths. And therefore, these events are mutually exclusive. Are not mutually exclusive. I'm sorry, not mutually exclusive. Right. So these two events are not mutually exclusive because there is an intersection. We'd actually have to subtract the intersection to get them equal. Okay, so they're not mutually exclusive. Okay, so another example here. Let's take a look at this. This has got us. So 7/10, is that equal to? So that's the probability of A union B. Is that equal to the probability of A 1/5 plus the probability of B 1/2? All right. Well, let's take a look. We're going to have to multiply above and below by 2 here. Right. So that gives us 2/10 plus 5/10, multiplying above and below by 5 here, plus 5/10, and that equals 7/10. And therefore, we can see 7/10 equals 7/10, so these are mutually exclusive. So the idea there being there's no intersection that we have to subtract, right? So this is the key idea. Is there an intersection? The key idea there is there an intersection? So that's all we're doing, is we're just applying this formula to find out whether or not there's an intersection. If they're not equal, they're not mutually exclusive. If they are equal, they are mutually exclusive because there is no intersection. That's the whole point, okay? Given no intersection. We can, of course, use all of that to find out. All we'd have to do is actually subtract 71 from 104 here to find the intersection, but we're not going to bother doing that right now. Okay. So remember, mutually exclusive events cannot occur at the same time. I'm going to do a couple of these for you real quick, and then I'm going to let you go and do them on your own, some classwork, and I think you'll get the idea here. Okay. So a bag contains 4 red marbles, 3 blue marbles, and 4 yellow marbles. You randomly pick a marble. The marble is red or blue. So are the events you got to determine if the events are mutually exclusive, then find the probability. So you're looking for so what is the probability of the marble being red, or the marble is red or blue? So the probability of the marble being red or blue probability of the marble being red or blue is 4 plus 3, that's 7 out of a possible 11, okay, right? So we want to find out if these are mutually exclusive, right? So we're looking at that as, is that equal to, right? So this is the union. Is that equal to the probability of red plus the probability of blue, right? So we got 4 out of 11 plus 3 out of 11. And that, of course, is equal to 7 out of 11. So therefore, these events are mutually exclusive. All right. You could, I'm doing it all together. I found the probability for us at 7 out of 11. But what we're looking at here is determining if the events are mutually exclusive. You can do that first. I mean, just by looking at it, you could determine by randomly picking a marble. You can't pick both a red and a blue marble at the same time. All right. And again, we'll look at it from the flip side on this one here. A bag contains 5 yellow tickets, numbered 1 through 5. The bag also contains 4 green tickets, numbered 1 through 4. You randomly pick a ticket. It is green or has a number greater than 2. Okay, so the 5 yellow tickets are numbered 1 through 5. 4 green tickets are numbered 1 through 4. Right? Now, just notice that some of the yellow tickets, 4 of the yellow tickets are labeled 1 through 4, and 4 of the green tickets are labeled 1 through 4. So it is green or has a number greater than 2. If you think about that, well, you can get number greater than 2 both on yellow and green tickets. So this is definitely not mutually exclusive. So we can determine first of all that this is not mutually exclusive, and we'll prove it. Right. So we're randomly picking a ticket. So the probability that it is green or has a number greater than 2. So the probability that it is green or greater than 2. Okay. So probability that it is green or greater than 2. So the probability that it is green, there are 4 tickets that are greater than 2. So we've got 4 tickets that are, 4 tickets that are green. And then greater than 2, we have another 3 from the yellow that are greater than 2. Okay, greater than, strictly greater than. So we've got 2 because we've got, we got 3 because we've got 3, 4, and 5. Okay, so greater than 2. So we've got 3 plus 4, so we've got 7 total, right? 7 total. So out of 9. Okay, so we've got 9 tickets, 5 yellow, 4 green. Okay, so that's 9 tickets total. We're including all the green tickets, so that's 4 of them. Plus, we're including 3 of the yellow tickets, okay, because they are greater than 2. So that's the probability that a ticket is either that it is green or greater than 2. And if we look at that now, we see, okay, well, the probability of being green, okay, as we said, is 4 out of 9, plus the probability of being greater than 2, right? Greater than 2, we actually have 3 yellow tickets that are greater than 2, and we have 2 green tickets that are greater than 2. So we've got 5 tickets that are greater than 2 altogether, right? And notice we now have to subtract the probability of being green and greater than 2. Right? And so you're subtracting that, you've got green and greater than 2. You've got 2 of them that are greater than 2. So 2 nines. So that's where we're getting our 7 nines from. Okay, so those are 2 examples that we look at, one mutually exclusive, one not mutually exclusive. When you notice that when you have an intersection, you're not mutually exclusive. I hope that helps, and I'll see you in class.